So welcome to lecture 4 for our Stat 479 multivariate high-dimensional statistics course. So just a quick reminder that homework number 1 is due Thursday, September 24th. So hopefully it's still a couple of still a couple of weeks away, depending on when you consume this lecture. But just wanted to give you a heads up for that. So that'll cover material from lectures 2 to probably 5 or 6. So today we're going to continue our discussion on the multivariate linear model and the multivariate linear regression. And in particular, I'm going to focus on a large part of today's lecture is going to focus, or this lecture is going to focus on the multivariate normal distribution. We're going to look at maximum likelihood estimation. So we've seen one approach for estimating the linear model, which is the least squares, the multivariate least squares. So today we're going to look at another approach in the setting where things are multivariate normal, which is a maximum likelihood estimation. And then I'm going to move on to how we solve these in practice, and one algorithm in particular that we'll go into a little bit of detail on starting today and then probably going into lecture 5 is this gradient descent algorithm. So recall that our general setup and framework, and remember that this is going to be really a core part of the course, is that we have some data. So this is typically going to be multivariate data, so p variables and one response because we're in the supervised setting. The statistical model that we have is the linear model. So you have y equals xb plus epsilon, and I've used this convenient matrix notation. So x is an n by p matrix, y is an n-dimensional vector, b is a p-dimensional vector that's the parameter of interest that we're trying to figure out from our data, and epsilon is our noise variable, and so e of epsilon is 0. And I talked about the fact that we can potentially make different assumptions on that epsilon, and so today we're going to assume that epsilon is multivariate normal, whereas before we assumed that it was just mean 0, and then we later assumed that it was homoscedastic, so it had variances that were the same. Today we're going to make the assumption that it's multivariate normal and see where that kind of takes us. And so the third component is the estimator or the algorithms that we use. So we've already looked a little bit at the least squares estimate. So that's just minimizing least squares, and it leads to a nice set of linear equations called the normal equations. So today we discuss a different procedure, which is the maximum likelihood estimation, which is a very general approach that we're going to see, that you've hopefully seen before, and we're going to see a lot throughout the course. And then we're going to finish with some analysis. That's just really looking at how well the estimator or the algorithms perform. So today we're going to be in a specific setting where we have our linear model, and we're going to assume that this epsilon is multivariate normal. So I haven't actually defined that, so it's okay if this notation doesn't completely make sense to you yet. We'll be more precise about it through the lecture. So MVN is the multivariate normal distribution, and it's defined by a mean vector, which we'll talk about shortly, and then this covariance matrix, which is going to be this positive definite matrix, and I'll talk more about that shortly. Okay, so we're going to begin by spending maybe 10-20 minutes on the multivariate normal distribution. So this is a very, very important multivariate distribution. Will come up a lot in this course because it has a lot of nice properties, and this is a course on multivariate statistics, so naturally it ties to multivariate distributions. And the multivariate normal distribution is probably the simplest and the distribution with the nicest properties. We'll see others as well, but this is the one that we're going to probably spend the most time on. And today that'll be one of the big focuses of this lecture. So its definition is if we have this n-dimensional vector, so this is now going to be a random vector y. We're going to say that it has y, which is this multivariate normal distribution. There's this parameter mean mu, and then the covariance matrix sigma. So the parameters here remember that every distribution has parameters associated with it. So mu here equals the expectation of y. So you can think about that as mu I equals the expectation of yi. And then sigma, which is this n by n matrix, that's the covariance matrix. So we can say that sigma ij is equal to the covariance of yi, yj. And we're going to assume that sigma is positive definite. So that just means that all of its eigenvalues have to be positive. All covariance matrices have to be positive semi-definite, but to kind of assume away like rank degeneracies, we're going to assume that it's positive definite. And yeah, this will be a typical property of full rank covariances. So first, let's look at what the PDF or probability density function looks like. So what does that look like? So I'm going to use this notation F to denote the PDF. And then we obviously have n variables, and it's going to actually be very convenient to write this in vector matrix notation again. So it's okay. So hopefully this notation makes sense to you. So we have this quadratic form in here. So inside the exponential, so this is n by 1 vector. This is an n by n matrix, and this is an n by 1 vector. So you're just going to get a number out of all that. That's simply just a quadratic form. Okay, and so that's what the PDF looks like. And so it's actually a pretty simple extension of the univariate case. So recall that if n equals 1, we kind of just have that there's two parameters here, mu and sigma squared. Then you're just going to get that so where we see the determinant of the covariance matrix, we're instead just going to have sorry, this is 1 over square root of sigma squared here, not sigma. And then in the exponential, we're going to have so it looks very similar with this sigma inverse here. We see this sigma squared on the denominator, so it has a very similar form to what we see in the univariate case, but now we kind of have matrix vector notation, and so this quadratic inside the exponential just gets replaced with a quadratic form involving n variables. Like in the univariate case, the multivariate normal in n dimensions has a lot of nice properties. So in particular, you can standardize and normalize in the multivariate case just like you can in the univariate case. So we'll say that Z is if we just have a zero mean and identity matrix. So here, this is n by n identity matrix. So what that basically just says is you take, so this is just n independent standard normals. And so the PDF is and you can easily see that this can be written as the product of that you can write this easily as just the product of the PDF for standard normals. So this is just n independent normals, and you can express any multivariate normal you can construct from this, and you can go both ways. So so if y here is if we have that y is multivariate normal with mean mu and variance and covariance sigma, then we have the relationship that y equals mu plus sigma to the half z. And so what this tells us is that and this is something that you're going to find really useful in homework 1 when you do your simulations. So if you want to construct any multivariate normal, you can easily just do that by starting with n independent standard normals, multiplying by the square root of the covariance matrix, and then adding the mean vector. And similarly, you can standardize and and you can also standardize, which goes the other way, which just says that z equals okay. So you can this is again just similar to what occurs in the univariate case. You can go back to your n independent standard normals by just by subtracting the mean and multiplying by or dividing by multiplying by the inverse of the square root of the covariance matrix. And then there are some other really nice properties of the multivariate normal. The first one is that we will call it closed under linear transformations. Which is that if A is an m by n matrix, then we can say that AY is also going to be a multivariate normal distribution with mean A mu and variance A sigma A transpose. We're going to use this property today and throughout the course. And just as a sanity check, we can see that the expectation of AY, because expectation is a linear operator, that should just be expectation of A times expectation of E of Y, which is A times mu, which certainly is consistent. And then if we have the covariance matrix for AY, this should be A times covariance of Y times A transpose. Again, because covariance is a bilinear operator. And so this is the covariance matrix, to be clear. And so this is just going to be A sigma A transpose. And so this is one really useful and unique property of the multivariate normal. You're kind of closed under linear transformations. The other thing that's really cool and very unique is that we can say so zero covariance implies independence. Remember that the converse is obviously true for everything, but this direction going from covariance 0 to independence is generally not true, but for the multivariate normal, it is true. So what that means is that if sigma ij equals 0, then you can say that xi and xj are independent. And then again, both of these properties are very unique to the multivariate normal, and they're true largely because like the multivariate normal is completely characterized by the mean and the covariance. So any dependence between variables is characterized by the covariance. And so if the covariance is 0, then there's no other way for there to be dependence between these random variables. Okay, and so we'll be using those properties throughout this course. In particular, the first property, we're going to see that being used today. So now we're going to return to the linear model. Remember, we made this assumption that that for today we're going to assume that the noise vector is a multivariate normal with mean 0 and covariance sigma. So another way to think about that is that we actually can write out the distribution of y completely, because we know that all that xb is the mean of the multivariate normal. So we have that y is a multivariate normal with mean xb and variance and covariance sigma. Sorry, let me just be clear. This is a sigma, not an epsilon. Okay, and so that's really our data for today. So now so because we've now specified the full distribution of y, we're in a position to work out what a maximum likelihood estimator is for y. So in the previous lecture, we calculated the least squares estimate because we didn't actually specify the complete distribution of the noise. We just said it was mean 0, and then we added some assumptions about it being homoscedastic. But you can only, and so with that, in that sense, like the least squares procedure doesn't rely on us knowing the whole distribution. But once we have the whole distribution, like we do in this case, there are many results to say that that maximum likelihood is the best thing we can do. So we know that the distribution of y is multivariate normal. We've completely know the distribution of the noise. So the way to actually estimate this quantity b is through maximum likelihood. And so what that involves is that we're going to get a different, now we're going to try to maximize likelihood. So okay, so what that involves is we need to use the PDF of the multivariate normal, which we saw earlier. So b hat here is going to be the maximum of f of y, and this is going to depend on this b, where this is the PDF of y. And recall that the PDF for the multivariate normal, we'll find it here, is given by this this expression here, so we can just write that out. So because our mean is xb, we can write this out as like this. And so, we're maximizing over B. So every other, we're assuming that we know our sigma. So that's not a known parameter. That's not a parameter of interest. And so we can re-express this. We can just drop that first term as it's just a constant. This is another thing we typically do with maximum likelihood. Okay, and then the other thing to notice is that so maximizing likelihood is equivalent to minimizing negative log likelihood. And what we'll see is that negative log likelihood often has a lot of useful information. We're going to do that a lot in this course, where the negative log likelihood actually contains a lot of information. And so often if we do maximum likelihood, it's often more convenient to see this through minimizing negative log likelihood. So that just means that we, take the log, which means the exponential goes away, and then take a and then just take the negative of that. So the negative here will go away, and so we get that this gives us okay, and this is very nice because this this should be an argmin, not an argmax now. So again, we are minimizing a quadratic form. And this is something that you will be doing on your first homework. So how do we do this minimization? So once again, this is nice. It's a quadratic form, so we can just differentiate and set to 0. So so any b hat satisfies equations. So if you differentiate and set to 0, so you can think about this objective as we can re-express the objective in this way, and then we take derivatives. You get that okay, so it's this is very similar to the normal equations, but you can see that we get something a little bit different. So these are these are modified normal equations. So this looks a little bit like the least squares, but we have, because of this covariance sigma, we have something that is a little bit different. So now what happens? We can actually show that the least squares can be a special case of this. So so this is the homoscedastic noise case. Then you can show that the ML estimate, so this is the maximum likelihood estimate, satisfies okay. So if we're in this setting where we're in the multivariate normal setting with zero mean and an identity covariance times some sigma squared, maximum likelihood and least squares are equivalent. So that's another interpretation for the least squares estimate, is that from a statistical point of view, it's the maximum likelihood estimate when you have a multivariate normal distribution with homoscedastic noise. And you're gonna see an example of that in the homework. Okay, so for now, we're going to assume that y is xb is multivariate normal with mean of xb and covariance of sigma squared I n by n. And so in this setting, therefore the least squares So the least squares and maximum likelihood estimates are equivalent. Sorry for the writing there. So now let's focus on the analysis. So using the extra knowledge that we have about y, we know that y is multivariate normal. You can actually deduce more than what we did last time. So what we did last time is we focused on calculating quantities like mean squared error, bias, variance, mean squared prediction error, and so on. What we can do in this instance is we can actually do a little bit more because we have distributional information about y, and that's going to in turn translate to distributional information about b hat. So okay, so in particular, we know that x transpose x b hat equals x transpose y. And once again, in the analysis phase, we want to say something about how b hat relates to b. And so if we assume that, and we also have that y equals xb plus epsilon, where epsilon is multivariate normal, mean zero, and covariance sigma. Sorry, we're in this homoscedastic setting, so what we can then do is if rank of x equals p, so x transpose x is invertible, then we have that b hat, again, this is a calculation that we've seen before, and so that so b hat is equal to b plus x transpose x inverse x transpose epsilon. Okay, so what we can actually do now is we can we can actually say more because of the fact that we know that epsilon is multivariate normal. So okay, so what that means is using using first property of multivariate normals, we can say that b hat is going to be a multivariate normal distribution with mean b, and then we're going to have that the covariance is going to be x transpose x inverse transpose. So you can think of this now as your overall A matrix, and then the covariance of epsilon, and then the transpose of that, which is x transpose x inverse. So this is using that second property. And so we know that the covariance of epsilon is equal to sigma squared I. And so what we end up with is that b hat is multivariate normal with mean v, and then the covariance is going to be sigma squared x transpose x inverse, because we get cancellation of the inverses. And so, some of these terms will look familiar to you. Recall that in the previous lecture we sort of showed that b hat had a mean of b, so it was unbiased, and then this expression sigma squared x transpose x inverse came up when we calculated the mean squared error, because that is the covariance. But now we know more because because the multivariate normals closed under these linear operations. You can say that you can say exactly what the distribution of b hat is. And furthermore, if you're interested in prediction, you can say that x b hat, you're going to multiply. Remember that you multiply the mean vector by the matrix itself, and then for the covariance you multiply both the left and right. You multiply the left by x and the right by x transpose. And so this is the hat projection matrix that we saw earlier. Okay, and so why is this relevant? Okay. So we can draw inferences and calculate confidence intervals for b hat and x b hat. So we know that b hat minus b is multivariate normal with mean 0 and covariance and then so if we want to say how close is b hat to b, which is what we're trying to do in the analysis or the inference stage. Properties of standard normals So, that's great because we can say what the distribution of any, so b hat minus b is a p-dimensional vector. You can say anything about what is the marginal distribution, what's the distribution of a linear combination of these parameters. If you want to find confidence intervals, you can do that very easily because we have this distribution. So we can do the same for xb hat compared to xb because we know the distribution. And it follows, and I mean, the essence of the reason why we can do this is because epsilon or the E or the noise variable here is a multivariate normal with mean 0 and variance sigma, and both maximum likelihood and least squares are linear estimators. So any linear estimator is going to stay multivariate normal, and so this allows us to basically draw these pretty powerful conclusions in the setting where things are multivariate normal. Okay, so now we're going to change tack a little bit and look at things more from a computational algorithmic perspective. So the question that I'm going to begin by posing is computationally, how do we find the least squares or maximum likelihood estimator? So in this particular case, it's quite nice because we can actually write things out in closed form. As we're going to see, that's generally not going to be the case, and we're going to see that as early as maybe lecture 6 or lecture 7. So there's a number of different ways to solve it because it's sort of a nice linear system with a closed form solution, which is rare and nice. But what I'm going to do is I'm going to show you an iterative algorithm that allows us to compute the estimate, and this is something that you will be implementing in your homework. And this is going to serve us well throughout the course. It's going to be an algorithm that we're going to see a lot throughout the course. So for least squares and maximum likelihood, if you assume homoscedastic noise, b hat is just the minimizer of this quadratic, and then I'm writing this down for about probably the 10th or more time. You end up with the linear system, which is the normal equations. the solution boils down to how do we invert a P by P matrix. So there's many approaches, and you can look into. There's courses, and there's also many books written about numerical linear algebra, and that basically addresses this fundamental question of how to invert a matrix. And you can say, well, why do you need so much effort on how to invert a matrix? And the reason is because inverting a matrix is one of the operations that we do in computational math and statistics so many times that finding fast ways to do that is a central question that, the faster you can do that, the more and more that we can improve computation. So you've actually learned how to do some of these methods are some of the things that you've actually done in high school. So you may have heard of Gaussian elimination, or it's sometimes referred to as Gauss-Jordan elimination. I don't know, maybe in high school or maybe in early university years, you learned about, when you want to invert like a 3x3 or a 4x4 matrix, you kind of, convert things to like row echelon form by trying to create zeros by looking at linear combinations of rows to try to create like upper triangular and lower triangular matrices. This is referred to as Gaussian elimination or Gauss-Jordan elimination because you're trying to basically create zeros in the matrix by taking linear combinations. That's actually a very standard approach for inverting these linear systems, and there are many, many more. And we're going to, I'm not going to spend too much time sort of focusing on other methods because I'm going to kind of introduce one method that I think is very widely used, and it'll be used not only for this particular setting, but throughout the course. So today we're going to focus on gradient descent algorithm, which is very, very general. We're going to see this actually a lot throughout, particularly the first half of the course, but just generally. I'm going to cover this particular algorithm because I think it's very probably one of the most widely used, if not the most widely used algorithm. And I think it gives a lot of insight as to just how do other algorithms perform as well. So I'm going to focus on gradient descent for solving these linear systems, and we're going to go through that in today and probably into lecture 5 as well. And this is very important to keep in mind because it's something that you'll be seeing on the homeworks on the first couple of homeworks fairly regularly, and again something that some of you may have seen this before, but for those of you who haven't, it's an extremely useful tool and something that's very straightforward to implement. So let's discuss gradient descent. So we begin with just any different. So we're in multivariate statistics, so we're going to be talking about multivariate functions. So f is a multivariate function, so it goes from Rp to R, and we're going to assume that it's differentiable. There's a term gradient in the algorithm, and so that's going to, it's obviously gradients are going to be very, very important here. we want to find, we're going to basically, we're going to assume differentiability. So our goal is to find a minimizer of this algorithm. And again, I'm using this notation element of because there's potentially more than one minimizer. So it's a function of B. Okay, so B is clearly in R to the P, and that's like our parameter of interest. And so the gradient descent update, which is just so simple to write and yet so useful, is that it's an iterative algorithm. So you start with some estimate and then you move to another estimate. So we're assuming things are differentiable. So this is the gradient, and it's the gradient evaluated at BT. So we can see it's an iterative algorithm. And this is something that you will implement, and it's so easy to implement because it's just such a simple thing to work out. As long as you can calculate derivatives, that's probably the main challenging step, is calculating derivatives. Here we have gradient. This is just the gradient, and so you know that the gradient is in R to the P. So because f is a function of p variables, the gradient is going to be a p-dimensional vector. Alpha t, we can say t equals 1 to infinity. That's the step sizes. So we're going to talk more about how to actually choose those step sizes in a reasonable way. But basically, and then you also have like some starting point. Obviously, it's an iterative algorithm, so it has to start somewhere. So you start with a starting point. Okay, so I'm going to give a little bit more intuition behind it in general in the next lecture, but let's see what this looks like for the case. We've been talking about the linear system, so or for least squares. So let's see what this looks like for least squares. So what for least squares, what we have is we're minimizing a quadratic. So our goal is so this is what our goal is. And so what does the gradient f of b look like? So we've actually already calculated this. And we're going to get that this is what the gradient looks like. And you can see that this is a p by n matrix and that this is an n by 1 vector. So this is a p by 1 vector. So then the gradient descent update is just so in our particular case, it's going to be and this actually has a very nice form. Things are not going to be quite as nice in other cases, and the reason why it's nice is because the gradient's linear. So you can actually write this out as a Okay, so we get and so similar updates are going to occur for maximum likelihood. If we have maximum likelihood where epsilon's multivariate normal with mean 0 and covariance sigma, we're going to get very similar nice update equations. Um, because we're minimizing a quadratic. Okay, so I mean we've got we've got a procedure that's seemingly very simple and nice, but we don't really know much about it at this point. So there's a lot of questions that come up. So, you know, so how do we choose the starting point? That's the first question to think about. The second thing is like how do we choose step sizes? So we have this whole bunch of step sizes. Okay, and we haven't really talked about how to choose that, and if we want to implement this gradient descent update, that's something that we certainly have to worry about. And then the last and probably most important question to think about, and one we're going to spend a fair bit of time like focusing on in the next lecture, is why do we expect this algorithm to converge at all? I mean, you know, I've just kind of seemingly pulled this gradient descent update from thin air. Why would we actually expect this to actually converge to what we want it to? So, you know, what we're trying to say is that we know that we have that we know that that's the any solution. This is, you can think about this as just the same as saying that the gradient of f of b hat equals to 0. So then why the gradient descent update is So this is the gradient descent update that we have. And so what we want to say is like, as t goes to infinity, does bt converge to b hat? And so, like we're trying to say is, and here we're talking about algorithmic convergence. So as you run more and more iterative your algorithm, does bt converge to b hat? And so, so I'll address this question in the next lecture, but that's something to think about. If you have the, I encourage everyone to kind of think about that question themselves before we go into that in the next lecture. So we have this update equation, and then we have this is the we know that every solution should converge to that. And so if this iterative algorithm works well, then as you take more and more iterates, then your bt should converge to b hat. And so why would you expect this to be true? And does it depend on the how you choose the starting point to be 0, or how do we choose the step size? If does it depend on these quantities at all, or is it just always true? And that's something that we're going to discuss in the next lecture. Okay. So that's it for this lecture. And once again, hoping these video lectures are proving to be useful to you guys. If there's anything that you're confused about, please feel free to email me and join the time when I'm available during a live session, which is Thursday 1 to 2:30. Okay, thanks very much. Have a good rest of your day.